पहले एक बार फुल दिखा देना अंदर से। अरे ठीक है, कोई फुल दिखाने की जरूरत नहीं है। जैसे टॉपिक स्टार्ट करें। हाँ 11 बज गए। हाँ बज गए, हो गया स्टार्ट। Good morning. Hello and welcome to the session. In today's session, we will be discussing about floating point number representation and error detection and correction code. I am Akshay Kumar, Associate Professor, and this session is primarily for MCA, BCA and Pgdca students of IGNOU. First year students, but other students can also watch the session. As usual, let's start this particular session with a piece of advice. Last time, in the last session, I requested you to download the program guide. Now I request you to please go through it also, because still I am receiving queries of the similar nature. Go through that particular program guide. You will find help for most of the topic which you want to ask us. And the first good help for any student is him or herself. So that help should be utilized. Okay, so I think with this we start this particular session, today's discussion, and we move. The reference material for this particular session is going to be block 1 unit 2 of MCS-12, and you can refer to this particular block very easily. There are slight changes in the slides which have been uploaded and the presentation, and you can find those differences while we are making the presentations. There are some unintentional errors and some intentional errors in that particular presentation. So let's start about the floating point numbers. Now, many a times we worry about floating point. Now, what is a floating point? What does it mean, a floating point representation? Right. So I just want to look into a floating point representation first. But I must know what a floating point number means. Okay. Now, in order to understand floating point numbers, let's look into the real numbers which we normally use. Okay. And the real numbers are something like, for example, 23.5. And if we represent that particular number in scientific notation, then it can be 2.35 into 10 to the power 1. Like that, I can represent the numbers either in scientific notation, the real numbers in scientific notation. Floating point representation is a direct replica of scientific notation which we use in general. Okay, and it consists of, as you can see in the slide, two parts, which is signed fixed point number, which happens to be the mantissa, and the binary point position. Why we call it floating point? Because the point position is not fixed. Suppose one number is 22.5, another can be 2.25, right? Another can be 2.35, 29.75, like that. The point position is varying, and that is what is the floating point. Now, when we are representing these numbers using computers, the mantissa can be either integer or a fraction. That is as simple as that. Now, the position. Now, what you really need to understand, that the position of binary point is assumed and it is not a physical point. This is what you need to understand, that this is not a physical point. It is just an assumed situation. Okay. And now, most of the time, we assume when we are representing floating point number, the position of binary before the number, and that makes it the that is the point number, right? So decimal number, this is what it is. Let's look this with the help of an example. Suppose there is a decimal number 67.94. Now we want to represent it in the mantissa and exponent form. Okay. Now easily I can represent mantissa as fraction and exponent as decimal. Okay, so this is how I can easily represent it. So what is going to be my, now this has to be a fraction. So how this fraction will look like? Fraction will look like 0.6794, and that is what it is represented over here. So 6794. Okay, what is the value of sign? Sign happens to be plus and plus happens to be 0. So 0.6794 exponent happens to be, the exponent side is going to be plus, okay, because the number is going to be 0.6794 into 10 to the power plus 2. So exponent is going to be that is 0.2 and the sign happens to be 0. Now exponent is just a number, right? It is not fraction. Okay, it's a integer form. Okay, so mantissa, if we represent the same number using an integer mantissa, then the number is going to be once again 6794. But look into the value of the exponent. If I want to represent it, and this particular number, actually it is, once again you can see the mistake over here. The number should be 6794 into 10 to the power minus 2, not 0.6794. 6794.0 into 10 to the power minus 2, and the exponent therefore has to be 1 followed by 0.2. Now that's a very, very complex representation if we talk about computer system, isn't it? Because in computer system, this is going to become very, very difficult algorithm to solve this kind of a situation. So what do we do? Let's look at this with the help of another example. So suppose the number is, this time decimal number is 10.25. So we want to represent this number with the help of binary floating point representation. So the equivalent binary value is going to be, if I say 10, it is going to be 1010, that you can calculate, and 0.25 is going to be 0.01. So the number is now 1010.01, and in binary we will always be representing the mantissa as a fraction. So what the equivalent value of this particular number is going to be 0.101001 into 2 to the power 4. That is, 4 is equivalent to 00. In fact, it should be, once again, second mistake. It should be 100. Okay, this has been corrected over here. So that is what you can see. So floating point numbers are represented in normalized form. Fractional mantissa does not contain 0 as the most significant digit of the number. So now this normalization is another concept. So we have represented this particular stuff, but when we want to represent floating point number, now this 0.1000, this number we can represent in many forms. For example, 0.010101 into 2 to the power 5 by adding another 0 before 1. That we can do. And then it will 2 to the power 5. But this is not the case when we want to represent the number. We want to represent these numbers in normalized form where the most significant digit is generally a 1. Now it may not happen in all the cases. We will talk about those cases and how to represent those cases in a slightly later slides or so. But technically what we are trying to say here, okay, so sign, which happens to be 0. Fractional mantissa, that means point will be assumed towards the left hand side. Okay, so and this is going to be 0.101001. Exponent happens to be, the sign of exponent is 0 and magnitude of exponent is 100. So this is the representation for the 10.25. But is it the correct representation or still something more is to be done? Okay, so let's go to an actual hypothetical 16-bit representation, and that particular representation we will try to explain the philosophy behind this particular representation. Now there will be one or two more concepts which will be coming up, and significant and mantissa are one and the same thing, but what we are going to add another concept or something called bias. So let's look into the representation now. So first thing is, what we are saying is, first we are representing the sign, okay, and sign is going to be attached to the significant or mantissa. The second thing which we will do for this hypothetical representation, we will represent exponent first and significant later. Now, is there any reason associated with it? Well, there is a major reason associated with it is comparison of two numbers. So we can just start from comparing the exponent, and if if an exponent is more than another exponent, that number is definitely bigger than the second number. You don't have to go to significant value and then check exponent like that. So that is why exponent is represented first. Okay, and the leftmost bit is sign bit, which we have already stated, of the mantissa. Mantissa or significant should be in normalized form. Why normalized form? Because it represents the maximal representation, right? So that is why the maximum you can represent with the help of it. Otherwise, we will talk about truncation error also later on, but you will find if we don't represent this in the maximal form, you will have more truncation errors. And the base of this number happens to be 2 and a value of 8. Now in this particular case, 8 is also slightly hypothetical because we normally add 2 to the power n minus 1. Okay, so let's not debate on that particular issue, but then a value of 8 is added. Why we have used it? Because this simplifies our arithmetic later on, and we have added 8 is added to exponent. Now this is called a bias. Why do we need to add exponent, some 8 into the exponent, and why not into the significant? Well, what we remember from our previous presentation and the same unit, block 1 unit 2, that in fixed point numbers, we represent fixed point negative numbers, or in fact fixed point numbers, with the help of sine 2's complement notation. So significant is definitely going to be in sine 2's complement notation. So why can't we do the similar thing to exponent? Well, once again, here lies the basic essence. Why we need bias? Once again, the comparison. Comparison of two exponents is much easier when we are representing it with the help of a bias rather than the binary 2's complement notation, where you will find if it is the magnitude, if you just compare the magnitude of minus 127, minus 126 with minus 127, you will find the magnitude, just the magnitude, not the representation wise, just the magnitude if you compare, then minus 126 magnitude will be higher, right? Similarly, minus 1 magnitude seems to be higher, so there will be different algorithm which you really need to represent, to use for this particular case. Whereas in the case of bias, it will be directly representable. It will be easily comparable number in that particular case. And there is another reason for this, and that is something which we will do when we do actual number. This is called subnormal numbers. Okay, so right now in hypothetical 16-bit machine, we don't have any subnormal number, so that is why, let's not to confuse you. So just the thing is here is that there has to be a comparison available to us. Now that all the things which I have spoken so far are somewhat hypothetical, they look, there had to be some examples for this particular representation. So let's look into the representation first and then the example of this particular representation. Right. So now what are the things which we are doing here? A normal exponent of 4 bits normally can represent exponent values between 0 and 15. Right? So you can represent the values between 0 and 15. So biased exponent changes that exponent range from, because we have added 8. So if we have represented 0 as an exponent, actually it is minus 8. Right? If our exponent is 7 plus 8, 15. So basically when we add 8 into it, it becomes 0. So the number range, the exponent range is going to be minus 8 to 7. Now this is a very important concept. Once again I am repeating this, that when I add bias, the range, right, 0 to 15, start representing a range which I desire the number to represent. Right, and over here it is minus 8 to 7 because the bias was 8, right? Suppose I have bias of 7 only, then the values would have been minus 7 to 8, right? So that is how this particular range or this particular exponent range is going to change in the binary floating point representation. Second thing you have to see here is a normalized mantissa. The leftmost bit cannot be 0 in general. Therefore, it has to be 1 in this particular representation. However, when we move on to another representation, you will find we can change this particular situation. Now, should we store this first bit or can it be assumed implicitly? Now, that's a question which we can answer. And many a times, since the first bit we are assuming that it has to be 1. Suppose it is not 1, then probably that is not a number with this particular representation. Okay, so if it is 1, so we can assume it implicitly. Okay, so if we can assume it implicitly, so the first bit, that means the remaining 11 bit. Okay, so we have 16-bit representation, 1 bit for sign, 4 bit for exponent. How many are remaining? 11 bit. So those 11 bit of Mantissa can actually represent 11 plus 1 implicit bit, which happens to be 12 bit total Mantissa. So this we are getting 1 additional bit, which is not bad, right? So let's look into some examples, and then if there is a need, we can discuss about that particular thing. Now, a hypothetical 16-bit representation. Okay, this particular thing has been, once again, you can make equivalent binary representation. This is a table of 2 starting from 2 to the power 0, 1, 2, 3 and 4. You can have it over here. Then on the decimal side, when you move towards the decimal side, 2 to the power -1, -2, -3, -4, -5, which happen to be the equivalent values, has been put over there. So let's try to represent plus 10.25, which we have represented earlier. So plus, okay, so the plus we have, right now there is nothing called plus. Let's yeah, some problem. Okay, so plus, okay, so what we have is 0, okay, 0, 1, 0, 1. Now I want to represent 8, right? So 2 to the power 3, 8, because I need to represent 10. So 8 plus 2, so this is 10. 0.25, there is a direct one over here. So this is 1010, right? Which is represented in 1010.01. Now, if I want to convert it into the hypothetical 16-bit representation, how big is my Mantissa? 12-bit. Now, what should be the exponent? This whole number should be fraction, and this first bit should be there. So I move 1, 2, 3 and 4. So my exponent happens to be 4, which happens to be 0, 1, 0, 0. However, this is not biased right now. Okay, my fractional Mantissa so far is starting from 1, right? So 1 followed by 0 coming over here, 1, 0 and 0, 1. So this whole Mantissa is over there now. Okay, now this one, which is shown in green, actually is not to be represented because it is now implicit as per our representation. So if it is implicit, it need not be represented. So my Mantissa becomes 0, 1, 0, 0, 1, and this 1 is already assumed, or it has to be there for this particular number representation. So what I am left with, the bits we will be representing, but first let's look into the Mantissa. Sorry, exponent. Let's look into the exponent. So what is the value of exponent? 4. What is our bias? 8, which is 1, 0, 0, 0. Now you can see the ease of computation, and we add 0, 1, 0, 0 into it. So what we get? 1, 1, 0, 0. So now effectively, now my Mantissa from 4 has changed to 12, right? So now my Mantissa, if you see, the number is 0 happens to be the sign. Okay, 1, 1, 1, 0 is the Mantissa, which happens, 1 here is the bias, and 1, 0, 0 is the actual the exponent, but while representing the number, it has to be plus 12. Okay, so this is 12 only, and the fractional Mantissa is going to be 1 happens to be the assumed bit or implicit bit. So we will have 11 other bits. So I already have 0, 1, 0, 0, 1, 0, 1, 0, 0, 1. Okay, now how many we are left with? 6 more bits. So they will be filled with zeros, and this is what is my floating point representation for 10.25. Let's take few more examples for this. Otherwise, we might get confused in this particular situation. Now we take another example of plus 6.375. Now 6 is going to be 4 and 2, right? 4 and 2, and over 2 to the power 0 is 0. Now 375 is less than 0.5, so it's 0 here. Okay, 0.375 is more than 0.25, so there is going to be 1 over here, and we are still left with 125. So 125 is this, so there is another 1 over here. So the number which we get now, 110.011. Okay, and this one is implicit. Okay, the first one is implicit, and the remaining 10011 coming from this zone will be taken. What is the exponent value in this particular case? How many bits we have moved? 1, 2 and 3. So exponent happens to be 3, okay, which is 011. And what we do in this exponent? Add a bias. When we add a bias, we get 1011, right? So this is the number now, 1011. The 1 which is the implicit bit, 100, then 11 and 6. Once again, least significant digits which have to be there to complete the representation. And the final example, once again, let's look into another example. Now this is slightly bigger, so you will realize the reason. So suppose I want to do it for 31.96875. So 31 happens to be 16 plus 8 plus 4 plus 2 plus 1. And 0.96875, you keep on adding 0.5 plus 0.2251, 0.75, 0.125, 0.0625, 0.03125. So all becomes 1. Then this particular number will be, the whole sum is going to be equal to this particular number. So this is what is the representation for 31.96875. Now over here, what is the exponent? 1 movement, 2, 3, 4 and 5. So exponent happens to be 5. Okay, and in the bias representation, it is 1101. Fractional mantissa in this particular case, how many? 4 plus 2. So 10 bits. Okay, so the 10 bit, and one of them is going to be implicit. So this green is once again implicit, and you can represent this particular number. This time, since 10 digits were already there, so you just need 2 more, that is padding of 2 bits, which is 00. So this is the number. So this particular way I can represent my number into the floating point number. But what I was talking about, that we can, suppose I get an unnormalized number, then how the numbers are going to be represented? Well, to know that, let us try to see what is the minimum and maximum for this binary floating point number range. So to do that, we will do some calculations first and then find the minimum and maximum. Well, the smallest mantissa value, what should be the smallest mantissa value? First one is implicitly 1, okay, and we have assumed 0.1, so this is the number representation. But IEEE is slightly different. I'll explain those differences to you a little bit later. So this is 0.1 over here, and followed by 11 zeros. Okay, so this is implicit, and all mantissa bits are 0. So that is the minimum one, right? Which happens to be 1 into 2 to the power minus 1, because this is what this bit position is 2 to the power minus 1. So we are just talking about the mantissa. We are not talking about the exponent so far. So this happens to be 0.5. Okay. What is the maximum value for the mantissa? The implicit 1 bit followed by all ones, right? So we get this particular stuff. Okay. Now to know this particular value, we can simply do a little bit of jugglery. We can add just 1 to it. Okay, and that actually is equal to 2 to the power minus 12 in this particular case, because this is the 12th location. So this is 2 to the power minus 12. Okay, and the sum of this will become 1. So this is equivalent to 1 minus 2 to the power minus 12. So this is how we have evaluated the values. Now let's look into the number range. What is the smallest negative number? Smallest negative number is going to be with maximum mantissa and maximum exponent. So this is going to be negative of 1 minus 2 to the power minus 12 into 2 to the power 7, roughly close it in terms of decimal. Lowest negative number. Now this is very, very important. Maximum mantissa and minimum exponent, which happens to be 0.5 into 2 to the power minus 8. Smallest positive number, 0.5 into 2 to the power minus 8. This is the smallest positive number, and largest positive number is into 2 to the power 7. Now look into these two numbers. That is largest negative number and the smallest positive number. If I roughly calculate 2 to the power minus 8, in fact not roughly, 2 to the power minus 8 is around 1 upon 256. And if I divide 0.5 by 256, right, it may somewhere will be 0.0002, right? So somewhere this is decimal equivalent we are referring to. So somewhere the decimal equivalent value minus 0.0002 and plus 0.002, there are nothing. No number can be represented between the two. You got my point? Between minus 0.000 roughly 2 to 0.0002, okay, zeros may be extra here and there, you can calculate that. But between these two values, there will be huge number of real numbers which go unrepresented by this particular format. Okay, so this is the weakness of the representation which we have been using. If I am using strict normalization only, then there is a range of number which go unrepresented. And this particular thing was covered in IEEE standard by introducing subnormal numbers. So in between the two, there will be somewhere subnormal numbers, and somewhere in between is going to be 0 also. Okay, in fact you will find there will be two representations of 0 in this particular representation. Okay, one will be positive 0 and one is going to be negative 0 as per the standard, and definitely that is what is represented in IEEE format. So now let us look into another issue as far as floating number is concerned. So it is about the precision of the number. Now precision is, if I can roughly put it in words, it is how precisely you can represent a number, right? How precisely you can represent the number using this particular format. So now if I am talking about the precision of number will be higher with bigger mantissa. So the bigger is the mantissa, the more chances of representing closer number to actual. Okay, let me show this particular thing with the help of an example. Now the example, let's start with the example with some numbers. Suppose I have just 2-bit mantissa, one is assumed and another is the 0 in this particular case. So this is 2, so this is the smallest number it can represent. The next number it can represent, now they can be smaller than this, but I'm just taking I'm starting from exponent 2, okay, and that is without bias. Exponent is without bias, just for the sake of demonstration. So if I start with that, so what I get, this is equivalent to number 2. 0.1 into 2 to the power 2 is 2. Then I multiply it with 2 to the power 2, what I get? 3, right? Okay, so this is what you move, actually when you multiply it by 2 to the power 2, you actually move towards the right twice. So you get a number 3. Now you move 3 times, you get 4. But 0.11 and 2 to the power 3, it becomes 110. It is 6. That means I cannot represent 5 using this particular representation. Moving further, okay, 2 to the power 4. So 1, 2, 3 and 4. This is 8, right? Then 2 to the power 4, 1, 2, 3, 4. This is 12. So between 8 and 12, I cannot represent precisely 9, 10, 11 and 12 with this particular representation. Likewise, it will go on further and further, right? So this is the whole issue. The lesser are the number of bits, okay, lesser are the number of bits by which I am representing a number, yeah, the lesser is the precision of the number, we will not be able to represent the numbers more accurately, or several numbers will be, for example, 5 may be truncated to 4 only, okay, similarly 7 will be truncated to 6 only, and many more numbers will be truncated to 8, 9 and 10 probably, right? So this is the way, I mean this is the problem of less number of bits if we use less number of bits in binary floating point number. And this is what has been pointed out here also. You can read this statement at your own convenience. Similarly, the truncation error is, suppose I'm utilizing just 2 bits, then 0.11 and 0.11. If I multiply them, what will I get? The answer will be 0.10, and that is going to be somewhere around 8, right? So this actually has to be, because 9 cannot be represented. I am ignoring the exponent in this particular case, so that's why you are getting this kind of a situation. But what you are seeing, that we will be losing a lot of valuable information when we are dealing with very small number of Mantissa bits. Okay, so the larger Mantissa bits are required, and on that basis IEEE designed several representations, okay, and standards. This is called single precision standard. Okay, in single precision standard, the total number size, or the number, can be represented using 32 bits. Okay, in that 32 bits, this out of these 32 bits, around 8 are used for representing the exponent, and 1 is signed, so you are left with so 1 is signed, 8 is exponent, so you are left with 23 bits. Now, interestingly, in this particular case, the highest exponent, now exponent is going to be biased, and that's what we will see slightly later. So exponent is definitely going to be biased, but the highest exponent, so if 8-bit representation, our exponent value can be 0 to 255. Now 255, if the value is, the n is not equals to 0, then we say that it does not represent a number. Okay, because the highest, because we need some value to represent infinity, and that is represented by the highest number, which can be represented by a machine using single precision. Okay, single floating point. That is IEEE standard. So suppose you are representing in C language, you are using float, then that is what you are going to get. Okay, so 255, okay, not equals to 0, and I suppose it is equals to 0, then it is minus or plus infinity depending on the sign bit. Okay, now moving on to, if E is between, exponent is between 0 and 255, that means 1 to 254. So 1 to 254, how many values? 255 values. So exponent divided by 2, right? So divide 254 by 2, how much you get? 127. So that is what is going to be the bias in this particular case. Okay, so that is what you will find. So the number is going to be, now please note, over here they have changed it to 1.n. We were using one implicit bit in the decimal side in that 16-bit representation. IEEE typically says that number is going to be 1.n multiplied by 2 to the power exponent and minus to 127. So accordingly, when I am representing the number, I have to make the adjustments into that particular form. Okay, now suppose the number, suppose I get a number where n is 101, the remaining 20s are zeros, and exponential happens to be 207. Then what is my actual number? My actual number, assuming that the sign is plus, it is going to be 1.101, because the Mantissa which has been represented, right? N is the Mantissa which has been represented. Okay, so 1 is the implicit one. So it is 1.201 multiplied by 2 to the power 207 was the actual Mantissa, and what we have to reduce from it, or what we have to remove from it, is the bias. Okay, when we were representing the number, okay, from okay, we'll take it other way around also. So the bias is to be removed, and what we will get? Plus 1.101 into 2 to the power 80. Suppose I get any number 0.1. Suppose I get to represent 0.1101 into 2 to the power 81. into IEEE number format. So how will I do the conversion? First I'll convert it into this particular form. So it becomes 1.101 into 2 to the power 80. Alright. And then my mantissa, what is going to be my mantissa? My mantissa is going to be 101 followed by 20 zeros because 1 is implicit. And my exponent is going to be 80 plus 127. 80 plus 127 will give me 207. So you can get both way how to convert the number, right? Now an interesting thing over here, suppose the exponent is 0. Okay, then we are getting the subnormal number which I was talking about. Okay, and the over here n is not going to be normalized, right? N is not normalized in this particular case because in the case of normalized number, 1 has been already assumed, okay, and the number has been represented. So n need not be normalized, and even our representation you got when the actual value which we represented may start with 0 because 1 was implicit in that particular case, right? So this is what you can see over here. Okay, so what you can see very easily is 2 to the power minus 126 because we have moved it towards this particular side 1 bit. So that is why we have enhanced our exponent value by 1. But on the other side, what you see, n is now normal and minimum number is 23. This 23 n's. So I'll be getting all zeros followed by 1. Okay, so now that is a subnormal number. It is not a normal number, but it is in the range which I was talking about. Minus smallest minimum number and smallest positive number. Between the two, sorry, largest minimum number and smallest positive number. Smallest positive number and largest negative number. Between the two, these subnormal numbers can be represented. And finally, the representation for 0. What you can see, plus minus 0 depending on the sign bit. So floating point numbers are not easy to understand, but they are very interesting. Okay, and most of the time, like if you get the feel of this, okay, you will be getting, I mean, many of you who are going to do numerical methods or numerical technique kind of a course, okay, that course also covers in detail, in-depth study about the floating point number. So you can also refer to those blogs and can study about this particular numbers. But these are very interesting set of numbers. The interesting part of these number is that number one, mantissa and the sign, they are related. Number two, the number technically has to be normalized, but they can be helps in not only representing the subnormal number, but bias also help in comparison of two numbers. Now, is the single precision number sufficient for floating point numbers? Well, no. There is double precision numbers. In fact, now quadruple precision format is also there, and octal precision formats are there. In general, if we compare typical floating point number of single precision to number of decimals it can represent correctly, it is 7 decimal to 8 decimals only. Whereas this double precision number can represent around 12 to 14 decimal digits that you can calculate. So octa precision number, octagon, that will, this quadruple will be another, this is 64 bits, that will be 128 bits, and then there will be 256 bits representation. So the more is the size, the more is the precision, the more accurately we will be able, represent a particular number within a floating point number. So this was the first part of my presentation. So we have talked about the floating point number. Now, in floating point number, what we have basically once again tried to see, floating point numbers basically are equivalent to real numbers. Okay, so they are somewhere down the line, somewhere equivalent to real numbers, and the real numbers then can be utilized. Can be represented in the form of some sort of exponent notation. from exponent notation, then you move on to represent these particular numbers from exponent notation in the form of mantissa and exponent. We represent exponent first because the exponent, once suppose both the numbers are positive, right, the exponent value can easily determine, right, easily determine which number is greater or smaller. We don't need to go to the mantissa. But if exponent is equal, then only we need to go to mantissa. In case of positive numbers, right, and in case of negative and positive numbers, well, it's going to be slightly different. So you got to study about this particular point. I have already tried to explain you in some basic sense, and you will be able to correlate this whatever we have studied to what you study during the block or extra reading or wherever you want to study. Now from the floating point number, let's move on to error detection and correction codes. Now these are another very interesting domain as far as computing science are concerned. Error detection and correction codes, basically their purpose is recognition and correction of errors during data transmission. And why do errors occur? There are some disturbances in transmission media or external environment that can cause. And what kind of errors do occur? Basically, what is the error? Error is 1 bit changes to 0 and 0 bit changes to 1. In fact, in networking, you will be studying about these codes very, you will be studying. But what we will be studying, what you use in computer hardware. Okay, many of you might have heard about term ECC RAMs, ECC error correcting and all those kinds of things. So what kind of technologies, these kinds of what kind of concept these technologies use is going to be discussed here. Now the very first thing which I'm going to discuss with you is the parity bit. Okay, now this is a very simple concept. You should enjoy this particular concept. Okay, one of the simplest error detection code, and now what we do in this, add 1 bit to binary data to make the total number of ones in that data either odd or even. For example, if data happens to be 0, 1, 1, 0, 1, 1, let's count the number of ones 1, 2, 3 and 4. Right? So we will add another bit as parity bit. If we want to add even parity bit, how many ones are already there? 4 ones. So the parity bit has to be 0 because we want to make the number of ones in this particular case as odd, and in this particular case they are even, in even parity, so they are already even, so we just add 0. So in 8-bit data we had only including the parity bit, we have everything as 1. Now if I want to do odd parity bit, there are 4, so by adding 1 I will have odd number of ones in the data as well as parity bit. Okay, so the parity bit value is going to be 1. Similarly, another case where data is 0, 0, 1, 0, 1, 1, 0, 1, the parity bit for even parity, once again, how many bits? 1, 1, 1. So for even parity, we will add parity bit as 1. So the data plus parity bit will have even number of ones. And odd parity is, if I add 0, then odd parity is going to be served. But how does it detect error? Okay, so consider the following 4-bit data. 1010, use odd parity bit becomes 1. So the overall data is, you add it here or before, it's up to the system, right? We'll see where, normally it is the topmost bit when 8 bits are used, 7 bits are used, 8 bit is onto the leftmost side. Okay, so if I say 0, 1, 0, 1, so odd parity is, so my data becomes 1, 1, 0, 1, 0. We transmit both data and odd parity bit to the receiver side, and when it is received as, suppose it is received as 10001, and obviously parity bit as is not changed as 1, there is 1 bit is an error. Now please note, these bits are, these codes are very simple codes, so normally they detect one error in 1 bit only, not too many bits. Suppose the 2 or 3 bits are in error, then it may or may not detect it. In 2 it will not, in 3 it may, in 4 it may not. So like that you can see. Okay, so odd parity at the destination will turn out to be 0, and the parity from the source which was transmitted, it has to be transmitted. So 0 and 1 are not same. So that is the flagging of error. So what we can say that there is an error in the data. So what is the error detection and correction? The objective of basic error detection and correction is data should be transmitted between a source and destination pair. It has reliably indicating error or even correcting it if possible. Now, the next thing which we want to know is the process. So, process of error detection and correction, how it starts. So, this is the source end, or on the source side. What we do, we apply error detection function to data at the source. So, and then we generate data plus error detection and correction code bits. We combine them as data. Store data and error detection correction bits together at the source. Then, if data transmission request transmit the store data as well as error detection and code bits to the requisite destination. Okay, so at the destination, then we receive it, data and this thing, data and error codes from the source. Then we apply on the data only. We apply the error detection and correction function once again to generate error detection and correction bit at the destination. Then we compare source and destination error code bits at the destination only. This is done at the destination only, and then try to flag or correct an error. So this is a simple process of error detection and correction. Some of the commonly used error detection function, the parity bit which I just spoke to you about, and the second is Hamming error correction code. Now we will talk about Hamming error correction code a little bit more, because this is one of the most important, and the way we are going to represent is once again a very practical way. Okay, so please be very attentive after the next slide. Okay, so Hamming error correction code happens to be Richard Hamming and Bell Laboratory decide this. We will just introduce this with the help of an example of 4-bit data. Let's assume a 4-bit data which happens to be D3 like this, and the basic idea is to divide these 4 bits into groups. So what we are going to do, please, this is the most important part of this presentation now about the error detection. The basic idea is to divide these 4 bits into groups such that parity bits value of those groups help in identifying error bits uniquely. Now, what is the best way in binary system is the position system. So if I say, okay, now this is important, this is the basis of grouping. Okay, so 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, and 2 to the power 3 is 8. Now, if I say this is my bit position 1, this is my bit position 2, 3, 4, 5, 6. So this is my complete data, which includes data as well as parity bits. That's what is the situation. So suppose my data bit is at location 3. On which parity it can cause error? Parity 2 and parity 1. Okay, so the positions which are very important for us, 1, 2, 4 and 8, and the remaining numbers are consisting of these values. Okay, therefore my parity bits are going to reside at position 1, 2, 4 and if needed 8. Okay, where my data bits will start? Once parity bit. So this is P1 and P2. So P1 will reside at this position. P2 will reside at this position. My data bit, first data bit will be residing at position number 3. Parity bit third will be residing in position number 4. Then data bit 2, data bit 3, data bit 4. Fortunately, we don't have any more data, so otherwise we would have what would have resided over P4, and then data 5, data 6 onwards we could have taken into consideration. Now look into the stuff here. So D4, 7 is 4 to 1, 4 to 1. So if there is an error, right, in D4, it will contribute to P3, P2 and P1. All the 3 places, all the 3 bits it is going to affect. So I can recognize that. If it is 6, it is going to affect only P3 and P2, right? Not P1, because 4 plus 2. This is how I am designing. I am grouping them into them now. Okay, D2 happens to be 5. So first that is P2, P3 and P1, no P2, and D1 in the case of P2 and P1. Now if any, now once again remember this particular thing, this particular code is when there is an error in only one bit of data or the code, any of them, only. So there are total 7 bits. Okay, out of these 7 bits, if any one of the bit is in error at the destination, we can recognize it. Otherwise, this particular scheme is not going to work. Okay, if more than 1 bits are in error. So let's look into example of it now. So suppose my data which is 1, 0 and 1, 0. So first thing is my bit positions, once again as we have done in the last slide, data bits happens to be 0, 1, 0, 1. Okay, starting from lowest bit 0, 1, 0, 1. At bit position 3, bit position 5, bit position 6 and bit position 7. Now let's use these bit positions to generate the parity bit. So what is the value of D4? D4 happens to be 1. So it can contribute to P3, it can contribute to P2 and it can contribute to P1. At all the 3 places, 1 each. Okay, 6. D3 can contribute to P2, so 0 is there. D3 can contribute to P2, so there is a 0, right? So this is 0. What about P5? So D2 can contribute at here, D2 can contribute here. Once again at 3 position it is 0, so the bit value is 0. It can contribute in P2 as well as P1 as we shown in the last slide. Okay, now what is the parity P1? 1, 2, so odd parity we are taking. How many ones? 2. So odd parity bit is going to be 1. So this P1 is going to be stored at, right, at this location. Okay, then P2 only 1, 1. So what is the value of odd parity? 0, right? And what is the odd parity in this particular case? 1. Right, because there are 2 ones, so odd parity is 1. So my parity bit which is generated at the source is 1, 0, 1 because of this particular data. And what is my data now? 1, 0, 1, the parity bit, the 0, this is data bit, the parity bit and the parity bit. So this is my data plus parity which is to be transmitted at the destination. Let's look into the destination situation. So I received the data. Suppose the data is received as 0, 1, 0, 1, 1. That means this particular 1 has actually changed. Instead of 0, it has been changed to 1. Rest all the data values and the parity bits are the same. Now using the data that is this D4, D3, D2 and D1. Let's generate the parity at the destination D3, D2 and D1. So once again we map it. 1 maps to D3, D1, all the 3. 6, 0 maps to 0, that is this position and this position only. 5 maps to this position and this position only. And D1, which happens to be in error, maps to this position as well as this position. Now, what are my parity bits now? 0 and 1. In this particular case, all the 3 bits are 1. So the parity bit is 0. In this case, okay, the two ones are there, so parity bit, to make it odd parity, it is 1. Okay, and for this the parity bit remains unchanged. So now what we see, this is the destination parity and this is the source parity. There is a difference between these two and these two. So what is the difference? Both are same, so put a value 0. If both are different, put a value 1. In both the cases, both are different, so we put a value 1. What is the value of this? What is the decimal equivalent of it? 0, 1, 1. What is the decimal equivalent of it? 3. That means bit position 3 is an error. Change it to, because it was 1, change it to 0. I have made the correction. Now correct data has been received 1, 0, 1, 0. Right? Slightly confused. So let's take another example. Okay. Once again, the similar situation, a different example. So pay attention once again. 1, 1, 0, 1, 0 and odd parity which we are using this time. So our data is 1, 1, 1 and 0. Parity bits are at P1, P2 and P3. D4 will contribute to this, this and this. It is 1, so we are putting 1 all the places. 6, D3 will contribute to P3 and P2. So both the cases, since 6 is having 1, data value 1, so 1 value is reflected at both the places. D2, once again 1, so both the places 1. D1 happens to be 0, so at both the places value 0. Alright? Alright? So odd parity in this particular case, 3 ones, odd parity 0, 2 ones, odd parity 1. Then we have 2 ones, so odd parity is 1. This is what my data. Now 1 1 1 comes from here, 0 is the parity bit, the data bit comes from here, 1 1 comes from here. This becomes my data plus parity, which is to be transmitted. Now data and parity is transmitted. Unfortunately, this time error is introduced in the 6th bit position. Data is received as 1010, right? So is there any error? So D4 once again contributes to this. D3 contributes to D3 as well as D2. Now in this particular case it is 0. Now you look into the D2. Once again you can see D1 and D2 same. But there is, because of D3, now you calculate the parity bit. This remains 1. This changed to 0 because there is 1 1. So this has to be 0. There are 2 ones, so parity bit has to be 1. So there the parity, right? So change in data introduced, error in parity. The parity bits are now 1 0. So let's compare them. 1 0 does not match. 1 0 does not match. So put a value 1. 1 1 are the same, so put a value 0 here. So what is my parity which is generated? The difference word which has been generated, 1 1 and 0, which is equivalent to 6, right? 4 plus 2, right? So 6 is basically which position? This position. Change this value to, from 0, it was already 0, change it to 1. So I am not able to just identify the error, but correct it also. Now this is the beauty of this Hemmings error correction code. This is error correction code. Parity was error detection only, but over here we are correcting the error also, but in single bit. Now there can be another situation where only the parity bit which is received is an error and data there is no error. So let's take that example also. Okay, so data is represented with the help of 1000, and you can now calculate at least these parity bits at the destination. So what we find, luckily in this particular case, all the parity bit happens to be zeros. Okay, and at the destination, what we receive, let's say the 4th, which is the parity bit, D3 is an error. All the data and everything has been received correctly. So what we will find in the parity bit, source parity bit and destination parity bit, there is a difference here. So our word, the difference word is 100. What is the equivalent value? 4, which happens to be this particular value, which says that the parity bit is an error. Data is correct. Simply use it. There is no need to change anything. So this is the way we have not only recognized the error, but we are able to correct errors in case when we are dealing with Hemming error correction code. Okay, compare it with the correction code or the parity bit, simple single parity bit, which was just an error detection code. So error detection and correction is a very important process, and bit positions can help us a lot. And I think with this example you can, now you are in a position to check your progress. So I have already included check your progress. You can solve these problems at your end and try to send answers to your friends groups also, where they will be helping you in seeing whether the answers are correct or not. And questions, once again, please ask questions about this. You can send your questions to many places listed in the program guide, and one of the places will be your coordinator place, so you can send your queries to your coordinator and they will be coming to the required person, going to the person who can answer those particular queries. Thank you for the time being. I hope you must have enjoyed the session. Bye for now.